Can everybody hear me all right with the mic? Yeah? Okay. Well, first I want to thank Philip and the other organizers of the conference for giving me the chance to talk to you today. One small note, Philip gave a talk on Sunday about information physics, and we talked a bit yesterday during the panel discussion about the future of the field. And I just think that we're actually in a revolution. And my sense is that the information theoretic approach to physics is just going to increase over the next 10, 20, 30 years. And it's going to cause us to rethink pretty much everything. It's not going to be a revolution in the sense of Newtonian mechanics or relativity or quantum theory. I think it'll be more a revolution in how we look at the same problem. So a revolution like the use of action principles that occurred in the 18th and 19th century, or the use of symmetry in the early 20th century. It wasn't an overthrowing of previous theories, but it changed the perspective we had on all of our theories. And so I think information theory is doing that right now, and will continue to do that. And one of the places where it's sort of already doing it is in the field of foundations of quantum mechanics. So that's what I'm going to talk about today. And I'm going to start with this, one of my favorite Jaynes quotes regarding quantum theory. So I'll just read it to you. He says, "But our present quantum mechanical formalism is not purely epistemological. It is a peculiar mixture describing in part realities of nature, in part incomplete human information about nature, all scrambled up by Heisenberg and Bohr into an omelet that nobody has seen how to unscramble. Yet we think that the unscrambling is a prerequisite for any further advance in basic physical theory. For if we cannot separate the subjective and objective aspects of the formalism, we cannot know what we are talking about. It is just that simple." So I subscribe to this notion that we need to unscramble the omelet of the epistemological and the ontological in quantum theory in order to make progress. And so I'm going to tell you today about my best attempts at unscrambling that omelet. And in particular, I'm going to try to answer the following question in the talk today, which is, what is the conceptual innovation of quantum theory from the perspective of classical physics? And so what I'm going to suggest is that a large part of quantum theory, not all of quantum theory, but a large part of quantum theory can be understood by adopting just one single conceptual innovation relative to a classical worldview, and that is that there's a fundamental limit on how much we can know about the physical states. Okay, so here's the picture. I'm going to start with a classical statistical theory, actually a few different examples, and then I'm going to add a particular restriction on what kinds of statistical distributions can be prepared in those classical theories. And I'm going to derive a large part of quantum theory in the sense of reproducing precisely the operational predictions of that theory. And you can then ask, well, what will be the status of the quantum state in this approach? So the wave function, or I like to represent quantum states by vectors in Hilbert space. And it turns out that these will correspond to probability distributions over the physical states that have non-zero width, and non-orthogonal quantum states will correspond to overlapping probability distributions. And so in my view, this provides strong evidence that quantum states should be thought of as states of incomplete knowledge, as like probability distributions over a physical state space, and not themselves states of reality. So two different quantum states are two different descriptions by an agent of a system. They don't correspond to two different universes, two different physical ways the universe could be. Okay, now I sometimes hear an objection at this stage, even if I've described the program in this very vague way. I'll get the following objection, that if you posit that there's something unknown, so you say, okay, there's quantum state's a state of incomplete knowledge about something deeper, so there's something unknown, but hang on, if you can never know it, then what's the use of positing it? Isn't that just futile metaphysics, and why don't we just get rid of this stuff? So to meet that objection, I want to use Plato's allegory of the cave. So you may remember Plato has this story where he imagines a bunch of prisoners that are in a cave, and they've been there their entire lives, and they're forced to look straight ahead at a wall, and there are some puppeteers behind them that carry objects between a light and the wall, and these objects cast shadows. And that's all the prisoners have ever known for their entire lives. And Plato says clearly the prisoners will mistake the shadows on the wall for reality. And the point is that we're like the prisoners. We see these objects around us, we mistake them for reality, but there's a deeper reality behind them. So in this, what I want to do with this allegory is imagine that the shadows are like the quantum state. And the objects are like some deeper reality of which the quantum state is incomplete knowledge. And now I want you to imagine that there's a prisoner here who is a scientist and sees all these shadows and comes up with a theory one day and says, it seems to me that all of these shadows, I could make sense of all these shadows by imagining that there's such a thing called the third dimension. And there's a single object which is three-dimensional, and what we are seeing are different aspects of that one three-dimensional object. And look, it makes a lot of sense. All these two-dimensional aspects sort of work well together in this theory. And my sense is that person would be doing good science. That person would be taking a large set of disparate data and unifying it with a single hypothesis. But another prisoner who said, oh, that's an interesting theory. I have a theory of my own, which is that these objects have color. And that color is totally irrelevant to all the shadows. So that person would also be positing something unknown and hidden. But the difference is that wouldn't be good science because the thing that was positive would have no explanatory power. And so my sense is that many people have a reaction against hidden variable models because they think that what's being posited is like the color of the objects here. But what I want to show you is what is in fact being positive is something like the shape. It's something that has explanatory power, and that's why it can still be good science. Okay, so here's a little summary of the research so far. So the game I'm going to play is to start with some classical theory. So for example, I can start with particle mechanics, and then I'll introduce the statistical theory for that classical theory. So by that I mean the theory of what you can know about the classical states. So there's not going to be any stochastic dynamics in this theory. The dynamics is still going to be the deterministic dynamics of the classical theory. But we're going to imagine that we're talking now about the probability distributions over the classical states, how those probability distributions evolve under the deterministic evolution of the physical states, how those probability distributions change if an observer comes to measure something or learn something about the systems, and so on. And in the case of particle mechanics, that theory is sometimes called Liouville mechanics. And then finally, the theory I'm interested in is what I'll call a restricted statistical theory for that classical theory. And I'm going to just introduce a postulate that limits the kinds of probability distributions that agents can come to know. Or I should say, that can characterize the knowledge of agents. And so in this case, I'll call the resulting theory restricted Liouville mechanics. And what I'll show you is that that theory is actually equivalent to a subset of quantum theory, which I'll call Gaussian quantum mechanics. And I'll define that eventually, but roughly speaking, if you take the pure quantum states whose profile and configuration space is a Gaussian, and then you consider all the measurements and all the transformations that don't take you outside that set of states, that is Gaussian quantum mechanics. So I'm going to be able to reconstruct that part of quantum theory, starting from this classical theory and adding the restriction. So if you're familiar with a Gaussian wave functions, or this sort of theory, then you might at first say, well, that's not very impressive. Gaussians are very simple mathematically. It's very easy to do everything. And then there's lots of other potentials I could write down that would give me wave functions that aren't Gaussian. So in what sense is this a large part of quantum theory? Isn't it really just a very small part of quantum theory? So I want to argue that it's a large part of quantum theory in the sense that it already contains most of the phenomena that we think of as somehow inherently quantum. So, for example, if you think of what I'll call the most basic quantum phenomena, things like non-commutativity of measurements, the existence of coherent superpositions, collapse of the wave function, the existence of complementary bases, the no cloning theorem, etc. All of those are already included in Gaussian quantum mechanics. quantum information theorists have discovered a number of phenomena that also distinguish quantum theory from classical theories. Among them, the quantum teleportation protocol, the possibility of secure key distribution, quantum error correction, improvements in metrological tasks like clock synchronization that make use of squeeze states. And again, all of these things are included in Gaussian quantum mechanics. You might think, for example, that entanglement is what's really innovative and key to quantum theory and has no classical analog. Well, what I hope to show you is that most of entanglement theory, again, is included in Gaussian quantum mechanics, including monogamy of entanglement, entanglement catalysis, all kinds of things. And then finally, for any experts in the audience, there's a number of formal features of quantum theory, such as the fact that a mixed state can be decomposed convexly into a set of pure states in many different ways, the fact that there's an isomorphism between states of pairs of systems and dynamics on a single system, and all these kinds of formal features also reside in this subset of quantum theory already. And therefore, the conclusion is that a great deal of what we take to be mysteriously quantum mechanical is included in this theory, and therefore, if you've got some conceptual derivation of this part of the theory, then you can make sense of these phenomena within a classical worldview. And these phenomena will appear less mysterious. So the other theories you can consider, you could start with bits. So these are just two-level classical systems, taking values 0, 1, for example. You can imagine you have a set of them, and you can imagine that they evolve. So really, it's useful here to think of a circuit. A circuit is a set of bits. They evolve. The dynamics is given by gates. So two of these bits could interact, undergo some deterministic transformation. And now I can imagine the statistical theory for those bits, which is just the theory of what I know. So some probability distribution over the strings, how that probability distribution changes as I pass it through the circuit, how it changes if I do a measurement of some of the bits, and then introduce some kind of restriction on how much you can know. And what you get by doing that, if you do it in a particular way, is something that is very close to what quantum information theorists call the stabilizer formalism for qubits. So qubits are two-level quantum systems. And the stabilizer formalism is like a discrete analog of Gaussian quantum mechanics. So now we're in a finite dimensional Hilbert space, but you can still define something that's like this subset of quantum mechanics, but quite a bit simpler. And although you don't get this theory precisely, you get something extremely close to it. And it certainly has all the same kind of phenomena. The theory that you derive has all the same kind of phenomena as the stabilizer theory for qubits has. So then you can go on, you can say, what about three-level systems? You can write down the statistical theory and introduce a restriction, and here you get precisely the stabilizer formalism for three-level quantum systems. So this case is even more analogous to the first one, where you're really getting part of quantum theory. I think it's interesting that you have this difference between the even and the odd dimensional Hilbert space, and I don't quite understand why that is. Another example I've looked at is optics. So there's something called statistical optics, which is the theory of probability distributions over different states of the electromagnetic field. You can add a restriction, and what you can get at is what the experts call linear quantum optics. And that includes a lot of laboratory experiments that use lots of different components, like phase shifters and homodyne detection and squeezers and beam splitters. And any experiment in the lab that involves those components is part of linear quantum optics. Okay, so that's essentially what's been done so far. But looking into the future, you might think, what if you started with electrodynamics, so charges and fields, looked at the statistical theory, added a restriction on what you know? Might you be able to get some part of QED, or something that's very close to some part of QED? Or even more ambitiously, start with some classical theory of gravity, such as general relativity. Try to determine what the statistical theory looks like, add a restriction. And perhaps you could, in this way, get some part of the true theory of quantum gravity, if indeed it's appropriate to talk about a quantum theory of gravity. So in a sense, what I'm talking about here is a way of doing a kind of quantization. It doesn't really get you the full thing, but it gets you part of the way there. All right, so once you've done this, you haven't got all of quantum theory, but nonetheless, you learn a lot. And one of the things you learn is how to categorize quantum phenomena. You can take a set of quantum phenomena that you find mysterious. So here's a set that I've drawn. My background is partly in quantum information theory, so maybe it's a quantum information theory heavy set, but it's a list of phenomena that, from a classical perspective, look surprising. And then you can ask how many of these phenomena fall in the category of things that do arise in one of these restricted statistical theories, and how many don't, and in fact can be proven not to arise in those sorts of theories. And so for this particular list, you find actually most of them fall here on the left. So I mentioned interference, noncommutativity, entanglement. These are things that fall here. On the right, you find Bell inequality violations. That can't be reproduced by these kinds of theories. You also find quantum computational speedup. Now, we're not sure that there really is a quantum computational speedup because the complexity theory is very hard, but if it exists, it definitely won't be found in these theories. Something called the Bell-Cauchy-Specker theorem, or the contextuality of quantum theory, falls on the right. And certain aspects of items on the left are on the right. So what I mean by that is, when I write down a one-word slogan for a phenomena, what I really mean is take that aspect of the phenomena that people have traditionally described as being surprisingly non-classical. So, for example, in the case of teleportation, people often say, if you don't know about teleportation, don't worry about it, but it's a situation where the quantum state in Alice's lab can be transmitted to the quantum state in Bob's lab. And even though it takes an infinite amount of bits of information to describe the quantum state, this is done sending only 2 bits of information. And so people say that's what's surprising about teleportation. Well, that aspect of teleportation can be reproduced here. So I won't have an infinite amount of information to describe a quantum state in my models. There'll be subsets of quantum theory. They'll require fewer bits to describe, but they'll still require more than 2 bits to describe, and yet 2 bits will be sufficient for transmitting them. And so in that sense, I say, look, I've reduced the mystery of teleportation because I reproduced precisely that aspect that people pointed to and said was surprising. Now, you can always say there's a new aspect that is surprising, which is that now, how do you do it for, the real case, where, you have all the details. So I don't have a model of the full teleportation protocol, but I would say that's quite different from, not being able to reproduce those features that people have thought of as surprising. And then there's some phenomena that it's unclear how to categorize. So quantization of energy, angular momenta, so forth, fermionic particle statistics. I don't know exactly where those fall. If I had to guess, I would say quantization is probably over here. Fermionic statistics is probably over here, but I don't know. So there's more work to be done. But the point is that once you've formed these lists, then from the perspective of this particular research program, attempt to interpret quantum theory, these phenomena don't appear so strange from a classical perspective any longer, whereas these are still very surprising. And so you're motivated to try to make this list longer, because it's this list that will help advance the research program. This is what we can't do at present. So you'd really want to make this list as long as possible, and then look at these phenomena and see if they suggest some principle in addition to the principle that I've already used, which is that there's a restriction on how much you can know, but some other principle that might be able to derive these sorts of things. Okay, so let me summarize, what the research program looks like. So first of all, the fact that these restricted statistical theories seem to have a lot of success in deriving part of quantum theory suggests that quantum theory should be understood as a kind of probability theory, not a theory about how things move and what exists, but as a theory of how we should reason about the world. And that's a view that's it's going to be well represented here today, I suspect. Here's just a few articles that support that point of view. And furthermore, quantum states ought to be considered as states of incomplete knowledge. And that's also a notion that many people have defended previously. But I'm going to go a bit further and say that it suggests that quantum states are states of knowledge of some deeper reality, like my example of Plato's cave. And that's where there's sort of, I think, fewer people who follow me into that corner of interpretation space. But this is my speculation as to what kind of reconstruction of quantum theory might be possible. So I'm imagining that there could be a pair of principles, the first being that there is some fundamental restriction on agents' capacities to know the physical states of systems. So that's what I've been talking about so far. But then there's some second principle which will involve some change to our classical picture of the world. And I don't know what that principle is going to be. I have some ideas, but I think it's fair to say it's not clear what that can be. But the hope is that together those two things, that this second principle could get me all the phenomena that were on the right of that previous overhead I showed you, and that together these could yield quantum theory. So I think it's interesting to explore possibilities for this second principle. We know, for example, that we can't understand quantum theory as a local hidden variable model. But the things about which quantum states could be knowledge are not restricted to local hidden variables. There's lots of other things that you could imagine reality being besides local hidden variables. So I think there's lots of possibilities for how to do this. And then finally, I'll note that, to my mind, this first principle is not itself satisfactory, because ultimately what we would really like is some principles that describe the way the physical world works, and not a principle that refers to agents. In my view, agents should come out, what agents can know should come out of your physical theory, should not be a postulate. So ultimately what I would like would be able to derive principle one from some principles about the way the world works, and that's very conceivable. The fact that there's a restriction on how much I can know about the things around me could very well be a consequence of the physical laws that govern me as an object. So ultimately, you'd want to derive principle one as well. So, okay, this is sort of the lengthy introduction that kind of gives you the big picture of what I'm trying to do. The rest of the talk is telling you in detail about some of these theories. But let me pause and just ask if there are any questions about this, because I find it's sort of more important to get the big picture right.
When you say restricted, do you mean
Yes.
a subset or something different?
I mean, so I'll tell you in detail the kinds of restrictions, but what I mean is, of all the probability distributions you could write down over the classical state space, only a subset of those are going to be possible probability distributions that describe an agent's knowledge. So an agent can't have arbitrary knowledge. An agent will only have knowledge described by some particular distributions. Yes? Not necessarily. I mean, I imagine that if indeed you could explain the restriction on knowledge that an agent faces by virtue of the physics that governs them, then any system that's trying to find out information about the systems around it will be faced by those same restrictions. Yeah. Yes?
Right. The other side of the table, you get the Bell inequality listed. I wonder if James had very strong opinions about that and other people followed. Is there anything that has changed there that this still pops up as a problem? And according to James, it was just misunderstanding what you mean by independent systems.
So I think what's changed since James made those comments is that people have come up with much clearer expositions of Bell's theorem and looked into it very deeply and clarified what the assumptions are. And in my view, it's solid. That you can explain Bell's theorem in such a simple way that it's clear that you cannot have a local and causal explanation of the correlations, the Bell inequality violating correlations. So I disagree with James on that point. Yeah. John?
It's clearly of very deep importance to try to relate the quantum world and the classical world. The picture I've got from you is to taking the classical world and altering it, damaging it, if you like, changing it, to try and get closer and closer to the quantum world. I presume that the ultimate aim you'll have, mine would be too, is to link the two sufficiently well that we can actually start with quantum and go back to the classical, get the classical world out, and start from the foundations. Is that part of your mindset? Or do you really see it as classical down to quantum?
Well, so I agree that ultimately classical physics should be a special case of quantum physics. So if I restrict myself to diagonal density operators and certain kinds of maps and so forth, I will get something that's, I like to think of it as classical probability theory is actually emerging from quantum theory. Those density operators on their diagonal are probability distributions. So it's not really the content, forces and the physics, but the probability theory that's emerging out of the quantum formalism. So yes, classical probability theory is a special case of the quantum formalism. But here I want to kind of, that's sort of I guess I would say the standard view, and I want to impress upon you that actually you can get quite far going in the opposite direction. That you can take classical probability theory, make a minor modification to it, which says you can't know arbitrary things, and get something incredibly close to quantum theory, which suggests that the connection is not quite as simple as quantum theory is the true theory of the world and classical theory is just a bad approximation to it. There's a lot of the structure of classical theories are maintained in quantum theory. So things like the symplectic structure of the underlying space, I'm going to argue that that kind of stuff seems to really be there in quantum theory. So the differences are not as great as we thought.
Let me not stop you.
Okay. Yes?
Comment further on what John, and maybe you said this, and I apologize if you have, maybe the shadows on the wall are classical mechanics.
Well, I kind of like the analogy to refer in particular to quantum theory, because I'm imagining, for example, that when you measure the position, that's one kind of shadow. When you measure the momentum, that's another kind of shadow. You can't measure both position and momentum. That would be like knowing the full three-dimensional object. But if there was an object for which you could only ever see a particular two-dimensional aspect and none of the others, then maybe that would be a little bit closer to the classical case, where you don't have choices of different things to measure.
I think it's a question. If you take a spatial solution of quantum mechanics
Yes.
and throw out the non-classical ones by using some condition of classicality,
Yes.
then you have a theory, but you have sort of holes in the theory. You don't have a full space, and you run into technical problems. For example, if you throw out a lot of solution of the Hilbert space,
Right.
you no longer can use all the nice features of it. Here, you're working in the classical world and putting restrictions and pulling out some states also, I imagine. Do you run into these technical problems? Is it a real problem, or is it easy to show that you have some consistent restrictions that don't cost us?
So the theories you've got a restriction on the statistical classical theory, which gives you what I'm interested in, and what you get out is something that's not all of quantum theory. So there's a restriction as well. But the theories that you get are really quite elegant. So for instance, the group of transformations that's possible is closed, and the set of measurements that you can do don't take you outside that, and so similarly the set of transformations. So it does have some nice mathematical structure. And it turns out that there aren't that many subsets of quantum theory that do have that nice mathematical structure. So for instance, in this case, the group of transformations is called the Clifford group, both in the discrete and in the continuous case. And you can ask, is there any group that's bigger than the Clifford group, but smaller than the full group of unitaries? And the answer is no. If I add anything to the Clifford group, I get all unitaries. So it's not as if there's going to be some theories between these theories and that include these theories and that don't include all of quantum mechanics. In a sense, next stop, quantum mechanics. So there's not a whole lot of these kinds of theories that have these nice properties. Okay, well, why don't I continue now with some of the details. How am I doing on time, Philip? Okay, great. All right, so I'll start with restricted Liouville mechanics. So I want to say this is joint work with Steve Bartlett and Terry Rudolph. Here we are at the Quantum Auto Body Repair Shop in Australia, and apparently they don't hire quantum mechanics, if you're wondering about that. Okay, let's start with talking about Liouville mechanics. We want to restrict the kinds of distributions over phase space we can have. So what is a good restriction to apply? And so I'm going to look to quantum mechanics for some clues on how to do that. So in quantum mechanics, we have an uncertainty principle. it tells us that the product of variances of position and momentum is restricted in a particular way. So here, this is the variance in position defined in the normal way relative to expectation values of Hermitian operators. So this is the position operator here. This is a density operator. If you prefer, you can substitute it for a pure state psi. This term here, CXP, is the cross correlation between position and momentum, defined in this way. So this might be a little bit more general version of the uncertainty principle than what you're used to, where you would just drop this piece here and say delta x delta p is greater or equal to h bar over 2. But this is a more precise version which can be saturated. And it refers now to quantum states, right? So it's a variance in the outcomes of position and momentum measurements that you could get for a particular quantum state. But now I want to use it to introduce a restriction for Liouville mechanics. So if I have a probability distribution over a classical phase space, then I can also introduce a variance in position, a variance in momentum, a cross correlation. But now these things aren't defined in terms of expectation values of quantum state, but rather just expectation values for that classical probability distribution. So I can do that, and then I can just demand that this quantity here be bounded below by h bar over 2 squared. And I'll get something that looks a lot like the quantum constraint. So let me do that. So basically, I'm making a new postulate, which I'm adding on to the classical statistical theory. And I'm doing it first for just a single particle in one dimension. I'll generalize it in a moment. But it says that the only statistical distributions that can describe an agent's knowledge are those that satisfy this uncertainty principle. I'll call it the classical uncertainty principle to remind you that these things are classical second-order moments for the distribution, and a maximum entropy condition, that the entropy of that distribution over the phase space should be maximal for a given set of second-order moments that satisfy this constraint. So out of all the distributions that have a given set of second-order moments, you can only know the one that maximizes the entropy. So it's basically knowing as little as possible consistent with satisfying this constraint. Okay. Note that h bar here is a free parameter of my theory. Okay, so I could have chosen it to be different from the quantum h bar. But it makes sense to look at the case where it has the quantum value. And it's basically, its role is to constrain how much you can jointly know about position and momentum in this theory. And so among the distributions with a given set of second order moments, it's the Gaussian distributions that maximize the entropy. So so I'm going to have only the Gaussian distributions over the phase space in this theory. So here's a cartoon of what we've got. So our distributions are normalized, they're positive, and they can have a Gaussian profile in position momentum. But the product of the variance in position momentum can't be too small. It has to fill an area of phase space that's on the order of h bar. So they could be equal. I could squeeze it out, right? So I could have more certainty about momentum than position. And I could do the limit of infinite squeezing. So I could, for instance, know the position entirely precisely, and then I know nothing at all about momentum. Or I can know the momentum precisely and know nothing about position. And these correspond to, in quantum theory, the position eigenstates and the momentum eigenstates. But what I can't know in this theory is both position and momentum simultaneously, and I can't have some arbitrary probability distribution over them. Okay, so now let's generalize to more than one canonical degree of freedom. And so I'm going to use, again, I'm going to take guidance from quantum mechanics. Here's a form of the uncertainty principle. Yes?
But you can have mixtures of those Gaussians, right?
There's going to be a limitation on what kinds of mixtures you can have. So if you, say, take the coherent states, the one that have equal variances, and you take a Gaussian mixture of them, you get another Gaussian state that now just has, it doesn't saturate the uncertainty principle. It's just consistent with the uncertainty principle. And that's going to be an allowed state because it has a Gaussian profile. But if I took a mixture of two guys here and here, then the overall distribution is not Gaussian. That mixture is not allowed. So
Mixtures of
Superpositions. Can you consider superpositions?
You can also consider superpositions. So for example, if I take a superposition of a bunch of position eigenstates, I can get a momentum eigenstate, because all of these states and that state are Gaussian states. So there's only certain convex combination becomes a partial binary operation. Only certain convex, not binary, but only certain convex combinations of states are allowed in the theory, and only certain coherent superpositions are allowed in the theory. Now that's anyhow. So that's one of the ways in which this isn't like the full quantum theory, which allows arbitrary convex combination and coherent superposition. Okay, so here's something that you may not be familiar with, but it's a very general form of Heisenberg's uncertainty principle. In my opinion, this deserves to be in all the textbooks on quantum mechanics, and it's a shame that it's not. So let me explain this equation. So this is just a matrix inequality. So really what it's doing is it's summarizing a whole list of equations. One, I could diagonalize this matrix here and set all the eigenvalues positive, and so I'd get a long list of inequalities. So it's just a convenient way of listing a large number of inequalities, and all those inequalities just involve second-order moments of the quantum state. This matrix here is called the covariance matrix. It contains the variances of the positions and the momenta of all the different particles. So particle 1 here, particle 2 here. And off the diagonal, it contains the cross correlations. So cross correlation between the position and momentum of the first particle, the position of the first particle and the position of the second particle, and so on. This term here, the sigma, is the symplectic form from classical mechanics. So on the block diagonal, it's this symplectic form. It's 0 everywhere else. And so the equation just tells me to add this with I h bar times the symplectic form and set that matrix positive. So now to convince you that this actually gives back the single particle uncertainty relation, consider the case where I'm just looking at the 1 degree of freedom. So I just have this 2 by 2 matrix. So then the inequality looks like this. I add these two matrices together, I get this. And now the condition that the eigenvalues be positive is actually equivalent to the condition that the determinant be positive in this case. So if I take the determinant of this matrix, I get exactly this equation, which is what I had before. And I won't convince you of it, but you can actually derive this from the canonical commutation relations in quantum mechanics. And it has all the restrictions on the second order moments for a given quantum state. So the obvious thing to do is to take the classical analog of that. So the statistical restriction for Liouville mechanics is just to define a covariance matrix, but now for your classical probability distribution, not for a quantum state. So now it's a distribution over the full phase space of n degrees of freedom. And you still have your symplectic form, and you set this matrix positive. Now, the I here doesn't mean that we're not talking about probability distributions anymore. Again, this is just a convenient way of summarizing a long list of inequalities, all of which refer to expectation values of positive probability distributions. Okay, so here's the form of the postulate in a little bit more general. So a Liouville distribution, this should be now over x1, p1, all the way up to xn, pn. It has to satisfy the classical uncertainty principle given here, and it has to maximize the entropy relative to the second order moments of that distribution. And again, if you ask, well, which distributions do maximize the entropy for a given covariance matrix, it turns out to be only the multivariate Gaussians. So gamma here is the covariance matrix. Z is a vector which contains, which describes the point in phase space. Okay. So let's consider a simple case where we just have two systems rather than one system. Then, for instance, among the valid distributions are products of Gaussians. So that's fine. But in addition to those uncorrelated distributions, I have some correlated distributions. So here's a particularly interesting one. It's a delta function in the difference between the positions of the two particles and the sum of their momenta. So it turns out that this variable and this variable are not canonically conjugate. Therefore, their variances can both be arbitrarily small. It's x1 minus x2 and p1 minus p2 whose variances can't both simultaneously be small. But these guys can be. And so this is just the analog of the famous Einstein-Podolsky-Rosen state, which involves perfect anti-correlation of momenta and perfect correlation of position. So this is allowed in the theory. Then you can ask, well, what about the transformations? What kinds of transformations would not violate this postulate that I've made? So it turns out it's the group of canonical transformation that have quadratic Hamiltonians, quadratic in the position momenta. So only canonical transformations are allowed because these are the ones that preserve the uncertainty principle. Okay, so the symplectic form is invariant under canonical transformations, and if I want to have a valid covariance matrix, the transformation has to be canonical or Hamiltonian. And the Hamiltonian has to be quadratic because it's only these that preserve the Gaussianity of the states. So I have a significant restriction on what kinds of dynamics are allowed. Now so the resulting transformations are sometimes called the symplectic affine transformations. That involves rotations in the phase space, squeezing in the phase space, that's the symplectic bit, and then translations and position momenta or combinations thereof, that's the affine bit. All of these are allowed. And the game I'm playing here is I'm saying, well, what would the universe have to be like in order for this restriction on knowledge to always apply? And the answer is, well, it could only have these kinds of dynamics. If you had other kinds of dynamics, then you couldn't maintain that restriction. Yes? No, that's essentially right. Yeah. And then you can ask the same question about measurements. What are the measurements that are allowed in this theory? So the measurements are going to be described by sets of response functions. So these are conditional probabilities, the probability for getting outcome k given that the system had position x and momentum p. And immediately you'll see that there has to be a restriction on these things because I'm allowed to prepare a state of knowledge for two systems, which is in the like the original EPR state, where you know everything about the relative position and the joint momentum. And so if I could come along to this system and find out exactly what its position and momentum was, I would immediately know what the position and momentum of the distance system was. So I would have prepared it in a distribution that was illegal, where I would know everything. And so more generally, if you come along with some indicator function on the left system, and you ask what's going to be the probability distribution that I infer for the right-hand system, and it ends up being just a time reversal of the indicator function. And so because the distributions on the right-hand system have to satisfy my statistical restriction, it follows that these indicator functions have to satisfy exactly the same condition. So again, you're going to be limited to measure things, response functions, whose area in phase space is bigger than h bar. Okay, so here's again the cartoon version. I can find a set of response functions, each of which is sort of a fuzzy measurement of position and momentum, and together they span the whole space. If I sum them up, I get the uniform distribution. Or I could start squeezing them to the point where, for instance, I learn only the position and I learn nothing about the momentum, or I could learn only the momentum and nothing about the position. But I certainly can't do a measurement that tells me both position and momentum, and I certainly can't do arbitrary measurements. Okay, now what happens after the measurement's over? How does the state update? So consider this case. Suppose you start with something where the momentum is perfectly known, and then you measure the position. So that's described by these response functions. Now in a classical theory, you would thereby afterwards know both the position and momentum. But that would be an illegal distribution in my approach. And so this can't happen. So you might be led to say, okay, well then no measurements are possible. But there's another way out. You could say, well, maybe it's the case that when I do this measurement, I perturb the system in an unknown way. So what would the final probability distribution after the measurement have to look like if this measurement was going to be reproducible? Suppose I got, say, this outcome here for this position. Well, it would have to be this distribution. Because if I know precisely what the position is, then I have to know nothing about the momentum. That's the only thing that's consistent with my restriction. So after this measurement's over, if it's reproducible, this is the only distribution that could possibly be prepared. And therefore, I have to imagine that what the measurement does is a sort of two-step process. The first thing is it does Bayesian updating. So you learn what the position was. But then there has to be a randomization of the momentum. So basically, some translation of momentum occurs to the system, but it's unknown to you. And if that happens, then you're going to be left with a distribution that's uniform over momentum which is what we want. Thank you. Okay, so I'm going to say a bit more about that in a moment, but first let me note that this unknown disturbance is what explains non-commutativity of measurements. So, for example, if I start with something where position is well known, I measure position and then momentum, then I get a perfectly predictable outcome for the position measurement. But if I first measure momentum and then position, the position outcome is now totally random. So we see that in quantum theory. We also see it in this theory because the momentum measurement here randomizes the position. That's what I just showed had to happen according to my postulate on the last slide. So we do have this kind of non-commutativity in the theory. Now, the concern at this point is, you told me earlier that the evolution was going to be deterministic, and then you just said that the momentum in a measurement is going to be randomized. Doesn't that mean you've postulated some stochastic dynamics? No. And I'll explain why. If I want, I can model the measurement device internally, dynamically. In the previous slides, I had modeled it just as an external intervention that was unanalyzed, not dynamical. But if I want, I can incorporate it into the dynamics. And when I do that, I'll show you that everything can be deterministic, and I can still explain this random disturbance to the momentum. So here's here's a schematic of my measurement device on the particle. It's measuring position. And now I want to model it in the following way. My system couples to a particle that's in my measurement device, and it couples to it via an interaction Hamiltonian that couples the position of the system. It's an XP interaction, X of system, momentum of apparatus. And this kind of Hamiltonian basically, because the momentum variable is the generator of translations in classical mechanics, this Hamiltonian will translate the apparatus particle by an amount that's proportional to the position of the system. Okay, so you turn it on for a certain amount of time, and then the amount that the apparatus probe particle gets displaced tells you what the original position of the system was. This is the kind of interaction Hamiltonian that von Neumann considered in his textbook. And so then what you have to do at the end is measure the position of that probe particle, and if as long as you knew where it was initially, you can then determine what the position of the system was. So we have to assume, therefore, that the probe particle was in a state of well-known position. Because if I didn't know its position, then I wouldn't be able to measure its displacement. And if I know its position, that means that I start out knowing nothing about its momentum. I'm just applying my statistical restriction to the probe particle now. Okay, so now here's the punchline, which is that if you look at the symmetry of this Hamiltonian, not only is it the case that the final position of the apparatus must reflect the initial position of the system, it's also the case that the final momentum of the system reflects the initial momentum of the apparatus. I can also think of this as a measurement by the system on the apparatus of its momentum. That's basically a version of Newton's principle of action-reaction. And therefore, the final momentum of the system is going to depend on the initial momentum of the apparatus in a significant way. But you know nothing about the initial momentum of the apparatus. That's what the statistical restriction ensured. No knowledge. And therefore, if the system gets translated by an amount that depends on the momentum of the apparatus, then you have no idea how much it was translated by. Therefore, you're left with complete uncertainty about what its final momentum is. Okay? So everything's deterministic. It's your uncertainty about the initial state of the apparatus that has infected the system and led you to be uncertain of the final momentum of the system particle. Okay, so this model can make sense of the Einstein-Podolsky-Rosen thought experiment, or reproduce the phenomenology of this experiment. Let me remind you briefly of it. You start with one of these EPR entangled states, relative position well-defined, total momentum well-defined. And then what EPR point out is that if you measure position or momentum on particle 1, you're able to predict the position or the momentum respectively of particle 2. And what Einstein wanted to emphasize is that there's nothing spooky or non-local about this as long as you interpret the wave function appropriately as a state of incomplete knowledge, not a state of reality. Okay, so what's the picture that this particular restricted theory provides? Well, the analog of the EPR state is the state of jointly knowing the total momentum and knowing the relative position. So the marginal on the second particle initially is just totally uniform over the phase space. And now when Alice measures, or person A measures position on particle 1, by virtue of this perfect correlation, she can update her knowledge about the second system such that she now knows what the position of the second system is. So by choosing to measure position, she's updated her knowledge of the distance system in a particular way. But she might have chosen to measure momentum, and then she would update her knowledge of the distance system in a different way. Now, I don't have to assume that anything about the physical state of the distance system has changed. It could be at a particular position of momentum, but it's just that Alice can't find out both those things. She has to make a choice. Do I resolve my uncertainty about position, or do I resolve my uncertainty about momentum? And so this is essentially what Einstein was pointing out, that you can imagine that it has all of its properties all along, and all that's happening with the collapse of the wave function is an updating of the agent's knowledge. Okay, so I'll finish very quickly by convincing you that, in fact, this theory I've just described at length does reproduce part of quantum mechanics. And the way to do that is using something called the Vignale Representation. So I'll go relatively quickly. If you're not familiar with the Vignale Representation, don't worry too much about it. There's something called the Weyl operators, which in quantum mechanics implement boosts and shifts, translations and boosts. And if I take something called the symplectic Fourier transform of the Weyl operators, I get a set of operators that are labeled by points in phase space. These are called the phase point operators. Both the set of Weyl operators and the set of point operators form a basis for the space of operators on the Hilbert space. So I can decompose any operator into a linear combination of these guys. And the Vignale representation for a density operator rho is just precisely its components relative to this basis. So it's the trace of rho times these phase point operators. And it turns out that it is, because these operators are Hermitian, the A's, this guy is a real function over the phase space. So I can represent every quantum state by a real function over the phase space. That's the Vignale representation. I can also do that for any projectors, so any elements of measurements I'm making. And you can find that the quantum expectation values, or the probability of getting a particular outcome in a measurement, is just given by the overlap of those two functions. So if these guys are positive, I can interpret this as the probability that the position is x and the momentum is p, and this as the probability that I get the right outcome in my measurement, given that it was x and p. And you can generalize this to many particles if you want. Okay, so the Gaussian quantum mechanics can be described as the subset, the states in Gaussian quantum mechanics are those states that have Gaussian Vignale representations. It turns out the Gaussian Vignale representations are the only ones for pure states that are everywhere positive. So I can interpret them as probability distributions. They're normalized, they're positive. And the critical fact is that if I look at the expectation value of some powers of position and momentum operators for some Vignale distribution, that gives me the quantum expectation value of the associated operator. And so the classical covariance matrix for a given Vignale function is just the quantum covariance matrix for the associated density operator. So because every quantum state satisfies my uncertainty principle, my covariance matrix condition, every Vignale function associated with a quantum state satisfies the classical version of that condition. And so it's a possible probability distribution in my restricted statistical theory. And so you can show that all of the functions in my restricted statistical theory are in fact Vignale representations for quantum states. You can then say, well, what about the measurements and the transformations? Well, you can define them in Gaussian quantum mechanics as those that preserve the Gaussianity of the state, and then they coincide precisely with the ones in my theory. And so you show that Liouville mechanics with the particular restriction I described is empirically equivalent to Gaussian quantum mechanics. All right. So when I was preparing the talk, I thought I would have more time to tell you about other versions of this theory, but I think this is enough to give you the idea of how these things work. I'm just going to skip over the slides for a discrete version of this theory. So this is, if you're interested, you can read this paper, but it's basically the same sort of trick for bits, and it shows that you reproduce. These are what the distributions look like. It's a discrete phase space now where position takes two values, momentum takes two values. You can work out the states, and you can see a lot of quantum phenomenology. and it reproduces some stuff for qubits. So let me just end with a couple of comments about phenomena that do not arise in these kinds of theories and where to go from here. So remember this slide here. There's a whole bunch of phenomena that you can get, and then there's some that you can't get. So I like to think that here's where the real non-classicality lies. And so, the key question is, well, in what ways do we have to change our classical worldview such that we can capture these phenomena? And so for me, Bell inequality violations and contextuality are really the key clues. And I haven't told you what contextuality is, but let me just say something that's a bit more general than Bell inequality violations. And furthermore, it seems to be an umbrella for lots of different notions of non-classicality that have appeared in the literature throughout the years. So I've tried very hard to make this list longer, but what I've actually been finding is that everything I add to this list tends to be a special case of the phenomena of contextuality. Now, since I haven't told you what contextuality is, I'm just going to make my final point in terms of Bell inequality violations and hope that some of you perhaps know about Bell inequality violations. So here's what I think is one of the sort of key clues for how to proceed. There's a tension between the Bell inequality violations and the fact that we cannot signal fasten the speed of light in quantum theory. So what's the tension? Well, the tension is that the Bell inequality violations prove that if you want to explain the correlations you see in quantum theory by a causal mechanism, then the causes have to travel faster than the speed of light. Okay, that's what Bell's theorem shows. However, if that were true, then you'd expect to be able to make use of those causes to send signals. And yet you can't. So it's as if there's some conspiracy in the universe. It says, yeah, there are these causes there, but sorry, you're not allowed to use them. And that seems uncomfortable. Why should it be that way? And so some people have argued that, well, really Bell inequality violations aren't true. There's loopholes and so forth. I don't really buy that. Some people have argued that, well, maybe soon we will figure out a way to send signals superluminally. I don't really buy that either. I won't go into the details. What seems more likely to me is that this tension needs to disappear. We need to come up with a way of thinking about the world such that it doesn't appear to be a tension anymore. So the analogy I like to keep in mind is in special relativity, prior to Einstein, if you laid down two postulates, one of which said that the laws of physics are the same in all reference frames, and the other of which said the speed of light is independent of the speed of the source, most people would say there's just no way to make those two things consistent. They're contradictory. It just doesn't make sense. And so Einstein's revolution in the way we thought about space-time was a way of taking those two postulates and relieving the tension between them. And so it seems to me that's the kind of thing we need here. And if we could find a worldview that relieved that tension, then I'm hopeful that we might be able to combine it with a restriction on how much we know in order to derive the quantum formalism. And I'll stop there. Thanks for your attention.
Thank you, Rob, for a fantastic talk. Questions?
So, quick clarification about your last point.
Yeah.
Given that you're pointing out that Bell inequalities are a special case of contextuality,
Yeah.
and contextuality doesn't have anything to do with spatial locality. Do you think that resolving this tension has anything to do with space-time at all, or does the solution have to be something orthogonal to that?
Yeah, I think it doesn't fundamentally have to do with space-time. I would say that, Bell inequality violations are just particularly surprising because they do violence to our notions of space-time, but it's just one special case of contextuality and whatever it is that we need to change. So maybe I don't know if I can say anything more that's particularly useful.
Rob, I just wanted to ask you something about something strategic, perhaps. I didn't quite get what your view is on how to proceed from here. Do we have, on the one hand, do we have to focus on those properties which you can't understand in a classical theory in the way you presented them, and for which we now know that they are truly quantum and not focus so much anymore on the things that can be given a classical reproduction, so that in that way we shall learn better what quantum theory is really trying to tell us? Or should we embark on or do you wish to embark on a research program to try and give all these other lists of items also some kind of classical reconstruction?
So the first, essentially, because I suspect that at some point the word classical won't apply any longer. At some point I'm hoping that there'll be an innovation where you say, well, clearly that's non-classical.
I didn't mean classical in the sense of classical mechanics, but
right.
in the sense of a classical ontology.
Well, okay, maybe let me just forget about the word classical and say, I'm interested in the first thing as a step to the second thing, where the second thing is maybe better described as an attempt to reproduce all these phenomena with some realist interpretation. So an interpretation that has an ontology. It may not be like the classical ontology, but it has an ontology. So I think that's the answer.
Okay, thank you.
A very small point. In all of the integrals or integration that you showed over dx, dp, can we assume that those are classical Riemannian integrations?
Yeah.
They are?
Yeah.
Okay, thanks.
Well, just a technicality of the vague integrals, right? Because you could have point. Oh, you're moving on. Use microphone. Oh, sorry. The vague integrals, right?
Why would I?
Well, you could have point masses, right? Which Riemann, delta functions, right? I think maybe that's what that's what was meant. But
True. So I guess I haven't said anything about those, technical details involving delta functions. Maybe I'll just say that, strictly speaking, position and momentum eigenstates aren't part of non-relativistic quantum mechanics. So in my model, I can consider states that are infinitely squeezed, and in the limit point may not be included in the model, but just as the position and momentum eigenstates are not included in relativistic quantum mechanics. But I have an analogy insofar as I have in my model states with arbitrary amounts of squeezing, just as in quantum mechanics you have states with arbitrary amounts of squeezing.
Time for one more question.
Mine is just a curiosity from someone else, practically nothing about quantum theory. But when you impose the equivalent of the generalization of the Heisenberg uncertainty principle,
yes.
I'm not surprised that you get those results. The question I have, can you derive the principle from basic rules of probability, of consistency, something like that? Because you postulate those and then you derive all those relations,
right?
And which don't surprise me. But the question, where do the constraints come from?
Right.
Could they come from first principles, or they're rather assumptions?
So there's sort of two places you could imagine the constraint coming from. As I said very briefly, ultimately I'd like to see the constraint coming from physics. So every agent in the universe is made up of physical systems. Those physical systems interact with other physical systems, and there's an action-reaction principle. And if there's an action-reaction principle, then it means that the agent, when trying to learn one thing, necessarily disturbs that system by virtue of the agent's very own physical state. And if the agent doesn't know the agent's own state, then the agent can't keep track of that disturbance. So I've tried to sketch out a vague way in which you could imagine that physical laws would imply that all agents can't come to know the states of systems around them. And in fact, it may be laws that we already have, just a kind of version of action-reaction. So there's that kind of derivation. But your question also seemed to suggest, is there some way maybe of phrasing these restrictions on knowledge in a way that maybe didn't, well, I'm going to ask a question that maybe wasn't there, but I have an answer to. So So I didn't show you the case with the discrete phase space, but that work is older, and the first restriction I came up with didn't make reference to position or momentum or symplectic structure or phase space at all. It was just the following. It said there has to be a balance between how much you know and how much you don't know. So for example, if it takes 2 bits to describe the state, then you can know at most one of those bits. And if it takes 4 bits to describe the state, then you can know at most 2 bits. And that felt very natural as a constraint on how much you know. I called it the knowledge balance principle. But in studying these things further, what I realized is that if you tried to generalize that to 3-level systems, you didn't get very close to quantum mechanics. It was better to use a principle that said, if you have a set of variables and you have a Poisson bracket for those variables, which is like a classical version of the commutator, it tells you which variables are canonically conjugate, then the constraint is you can only know a set of commuting variables, commuting relative to the Poisson bracket. So that's a constraint that actually makes reference to the structure of the phase space. And it did a much better job of deriving quantum theory than my original constraint did. It was the one that generalized well. So I've now kind of given up on this knowledge balance principle, even though it seemed very nice and kind of purely information theoretic, in favor of principles that actually refer to the underlying structure of the phase space. So all I can say is that this is what seems to come out. Perhaps it could still be possible to come up with a more abstract principle that doesn't refer to symplectic structure, but I haven't got one.
Speaker again.